In this lecture, we will talk about how to evaluate certain complex contour integrals. And typically, the curve gamma will be a closed contour, something like this. Now, from the Cauchy integral theorem, we know that if f is analytic inside here, then this integral is automatically 0. So the interesting case is really when we have some kind of singularity of f inside. So let's start with a case where we have just one singularity here at the point z0. Then we first note that by the Cauchy integral theorem we can deform this contour without changing the value of the integral. So we might as well assume that we're integrating along a circle around that point. And we call the circle gamma r, where r is the radius of the circle. Then. So we'll can rewrite it in this way. And then we also know that this function f can be expanded in a Laurent series, which then looks like this. And if this circle here is sufficiently small so that it's inside the radius of convergence of this power series, then we first of all can replace f by the power series and then move the summation outside the integral. And then we get the following expression for the integral. Yes, and this kind of integral, we have evaluated them before, but let's do it once more. So the idea is that once we have a circle here with radius r, you can parameterize by putting z equal to z0 plus r times e to the it. And then this integral becomes the integral of from 0 to 2 pi. And this expression now becomes r to the j and e to the ijt. And then we, instead of dz, we will get r times I e to the it, and then dt. And then you see that you get a function of the type e to the I j times j plus 1 times t up here. And as long as j is different from minus 1, the primitive function will be periodic with the period 2p, and then this function will evaluate to 0. So the only case where you get something non-zero here is when j is equal to minus 1. And then you see that this whole integral will just be I, and the integral will be 2 pi I when j is equal to minus 1 then. Well, when j is equal to minus 1, and 0 when j is different from minus 1. So the conclusion is here now that although this sum is formally infinite, there will only be one term different from 0, namely the one when j is equal to minus 1. And so then this will sum up to this constant 2 pi I times the coefficient a minus 1 in the Laurent expansion. So obviously this constant a minus 1 is important for integration, so we have a special name for it. So make a definition here now. A minus 1 is called the residue of f at the point z naught. And we denote it by res of f z naught, or if f is understood just like res of z naught. So this is how it looks when we have just one singularity. If we have, say, several singularities in here, then one can deform this contour gamma in the following way. We'll get something like this. Sorry. And then in the limit case, these corridors here will shrink to just lines, and then both the contributions, when you go this way and that way, they will cancel out. So in the end, you will see that the contour integral over this with these four singularities will just reduce to the sum of four integrals over small circles around these points like this. And this is really the basis for the Cauchy residue theorem. Which states then that if we have a closed contour like this, an orientation this direction, and we have an analytic function which has just a finite number of singularities inside the contour, then the integral of f of z dz over the contour is just 2 pi I times the sum of the residues of the function f at these singularities. So you sum over k, which is and where you have k singularities like this. So if you want to compute integrals, then it's obviously important how to compute these residues. So let us start with the case when the function f just has a simple pole, which means then that the summation here can start from -1 So how do we compute the coefficient a minus 1? Well, the idea is now that all terms here are regular at the point z naught, except the first one here, which gives a simple pole. So if you multiply this function now by z minus z naught, you will get a completely regular function. It will start with the constant a minus 1, and then the next term will be a0 times z minus z naught, and then it will go on like this. And then you see that if you just now take the limit of this expression, then all these terms here will go to 0, and you're just left with the residue. So you arrive at the formula then that the residue of f at the point z naught is equal to the limit z tend to z naught of the expression z minus z naught times f of z. In particular, if the function fz is a quotient of two functions, let's say it's quotient of p of z and q of z, like this, and suppose that Q has a zero of order 1 at the point Z0. Then we see that this expression here now, for the residue of f at Z0, it can be written as the limit Z tend to Z0 of P of, Z minus Z0 times P of Z divided by Q of Z. But now if Z0 is a zero of Q of Z, then you can rewrite this in the following way. We rewrite it as P of Z divided by Q of Z minus Q of Z0, and then here in the denominator of the denominator we have Z minus Z0. So this is just because Q of Z0 is 0, because this was a 0 of the denominator, and I have moved this factor down here then. And now we see that we can actually compute the limit by the quotient rule. So this will then simply be P of Z0. And down here, the limit of that will be the derivative of Q at the point Z0. So this is a usual expression for the residue of this function f when it's of this form. If we have a more complicated function where the zero is not, or the pole of the function is not of order 1, then one can do a similar thing, which is slightly more complicated then. So suppose that f of z is equal to the sum, j goes from minus m to infinity of a j times z minus z0 to the power j. So this means that the function has a pole of order m at the point z0. Then the formula that you get for the residue of f at z0 is then that you can compute it as a limit when z tends to z0 of 1 over m minus 1 factorial times the m minus 1th derivative of the function z minus z0 to the power m times f of z, like this. So you see that this formula generalizes what we have here. If m is equal to 1, the derivative here will disappear, and the factorial also. And the proof of the idea is really the same. If you have more terms with negative j here, you have to multiply by a higher factor to get something which is non-singular. And then you have to take the derivative a certain number of times to extract the coefficient of coefficient a minus 1. So let's now look at an example of such a contour integral here now. So we consider the integral of dz divided by z to the 4th plus 1 over a contour gamma, which in this case now will consist of a semicircle here with radius 3. So this is point 3 here now, and this is point minus 3. And so you have one part which is along the real axis, and then you have this semicircle like this. So how do we compute this integral then? Well, the Cauchy residue theorem tells us that we must find the residues of this function which lie inside this contour, and then compute the corresponding values then. So you see that this equation then or z to the fourth equal to minus 1. It has 4 zeros, which lies something like this, the complex plane. And of course, only 2 of them lie inside the contour. And the formula for these 2 zeros is just we can call one Z1, which is equal, this one is equal to e to the power I pi divided by 4 then. And the second one, Z2, will be equal to e to the power I 3 pi divided by 4. And then we have similar expressions for these 2 also, but we don't need them for this integral. So what will be the residue of this function? Well, 1 over z to the fourth plus 1 at the point e to the power I pi divided by 4. Well, we have the formula telling us that if we regard this as a quotient, then we should evaluate the numerator at this point and the derivative of the denominator at the same point. So since this function is just 1, there's nothing to evaluate. Here we now get the derivative of this will be 4 times z to the third. And so this should be evaluated at the point e equal to z equal to e to the power I times pi to the fourth. And so this will be then equal to 1/4 times e to the power minus 3I pi divided by 4. And similarly, we will get a residue at the point e to the power I 3 pi divided by 4, which will then be the same function here, evaluated now at the point e to the power I 3 pi divided by 4. Yeah, and when you evaluate this, you get 1/4 here, of course, and this expression to the third, that will give you 9 pi divided by 4 here. But since this is the imaginary exponential function is periodic with the period 2 pi, we can write this directly as e to the minus I pi divided by 4. So when we evaluate this to the third, it will be e to the I pi divided by 4, but since it's in the denominator, we'll also get a minus sign here now. So we're now ready to compute this integral. It will be equal to 2 pi I times the sum of these 2 residues then. And, well, if you move the 4 outside here, we see that we get pi over 2 times I. And this you can now write as minus 1 plus I divided by square root of 2. And this expression can be written as plus 1 minus I divided by square root of 2. And now we see that the real parts here will cancel, and inside here we'll get minus 2I divided by square root of 2. So the minus I together with the I outside, they will just cancel out, and we will be left with just pi divided by square root of 2, which is the value of this integral then. Now this residue calculus is not just useful for computing complex integrals. You can actually use it to compute real integrals also. So let's consider now, as an application of this, the integral of from the generalized integral from minus infinity to infinity of dx divided by x to the fourth plus 1. So this is a completely real problem, but the complex method here will solve the problem in a very neat way for us then. So the idea is that this integral can be interpreted as the complex integral. Well, first of all, let me say that this is, of course, the limit when r tends to infinity of the integral from minus r to r of dx divided by x to the fourth plus 1. And this integral here can be interpreted as the complex integral over the complex contour, which in this case is just an interval on the real axis. And then you have dz divided by z to the fourth plus 1 up here. And so it's actually the limit of this kind of contour contour integral that we want to compute. And now if we return to this picture here now, then we see that the fact that we use the circle with radius 3 here doesn't really influence the integral here. If we would have used the circle with radius 10 or 100 or 1,000, we would have got exactly the same value of the integral here because it only depends on what happens at these 2 points. So the idea is now that we consider a limit situation. We have here a semicircle gamma r here, and here we have the interval from minus r to r. And then we note that the contour integral over this curve here will always give us the value pi divided by square root of 2. However, it's easy to see now that the limit of the integral over gamma r over the semicircle here of dz divided by z to the fourth plus 1, this limit will be 0, simply because the denominator will go to 0, essentially like 1 over r to the fourth, but the length of the curve will only grow like 2 pi r, and therefore this limit will be 0. So the conclusion is that this limit can actually be written as the limit when r goes to infinity of the sum of these 2 integrals here now. Simply because this term tends to 0. And together this is then a closed contour which can be evaluated by residue calculus. So it will again be equal to 2 pi I times the sum of the residues inside here. Well, the residues at the point e to the I pi divided by 4 plus residue at the point e to the I 3 pi divided by 4. And again, by the same computation as up here, this will be equal to pi divided by square root of 2. So we have actually computed this integral Of course, this can be done with real methods also, but it will take the rather cumbersome partial to split this into partial fractions then. And this method is really much easier. And of course, there are also examples of function here where you can evaluate this kind of generalized integrals without, or where you cannot really find any nice primitive function. So this kind of technique will solve many integrals that are really difficult to handle with just real techniques.